My name is Zuhen Lin. I'm from NXP Semiconductors. As a device owner in a semiconductor manufacturing operation, it is critical to maintain product yield, cycle time, and quality due to its costly and complex processes. Any yield issue can raise delivery concern and require risk mitigation. In this case study, I will demonstrate how to use JUMP predictive modeling platform to make advanced decisions in semiconductor manufacturing operations. Here is an example of semiconductor wafer fab process flow. We start with 25 silicon wafers in the wafer lot. All 25 wafers will go through various processes to grow dielectrics or conducting material. Then it will be patterned to make into integrated circuitry within a die. In this case study, the technology involved more than 300 process steps. It takes about 9 weeks of the cycle time to finish the wafer, and it will be patterned so we can continue and send it on. But before the wafer will go to the oversee for the circuitry testing, you need to pass the wafer acceptance test, also known class probe here. Those are class probe will test individual device to ensure the health of each of the wafers. If the wafer are healthy and send it on, in this case overseed, then it will receive the unit probe test. At this time, the test is performed on each of the individual dies. So the entire integrated circuitry will be tested. So all die are tested, and they are either categorized into a passing bin, or it will be in one of the various failure bin. The white one is the good passing bin here, and you can see some different color here for the fail bin. So besides tracking the yield for my part A here, and we also tracked the bin performance. In this case, I'm going to show you bin 6. It is one of the bin that we had some problem recently. And this is the trend chart for the normalized bin 6 fallout. And you can see that this statistical bin limit we calculated based on the historical data. And this line represented if any wafer, which is each of the dot on this chart, if any of the wafer exceed this bin 6 criteria, it will be a wafer scrapped. It doesn't mean it's a 0 yield to be scrapped. It will be a scrapped. So you can see that recently in the yellow zone time zone, we have a lot that suffers many wafer being scrapped because the elevated bin 6 issue. There's some other lot, it looks okay, it didn't exceed the limit, but it's also elevated. So the management come in say, are we okay? Do we know the health of our wafer for part A? So in order to answer the question, I have to make a few decisions. First of all, that I have 150 wafers from 6 different lots. They are at end-of-line class probe. So they have the class probe data, but do we want to send the lot on to oversee for the unit probe? Are they going to suffer the bin 6 scrap? So that's first things I need to know, and I need to make a decision. Should I send it on? Are they at high risk or not? Secondly, if they do have suffered the yield loss, but not to the scrap level, how many wafer are impacted? How many die are we going to lose? And am I going to cause the customer line down because we cannot deliver the dies, the wafers on time? Very last, as a device owner, I need to know what maybe shift in line. Although it didn't fail for class probe, but maybe there are interaction between the class probe parameters. They are responsible for the elevated bin 6 fallout. So I need to know, so I can give the recommendation for the inline processes engineers, anything that we can do to help maintain the good quality of the die of the wafers. So what I need here is I need a predictive model to help me with the risk assessment in this situation. Okay, so the first step of building a predictive model is to define my responses and predictors. I'm going to use the class probe parameter that we collect from each wafer. Because we collect more than one site, I'm going to use the wafer median for those class probe. We have total 173 continuous factor here. They have some autocorrelation among those 173 factors because a transistor, we are going to extract the threshold voltage, the I said drive current. So there's some autocorrelation among those 173 parameters. And for the response, obviously, we are going to use bin 6 fallout here. We have total of more than 2,000 wafer data in my database. So I'm going to use all of them. That the normalized bin 6 fallout is the continuous response I'm going to use. And you can see that this is the histogram of my normalized bin 6 fallout pattern. And this is the statistical bin limit. Anything above, I scrapped, right? But I want to have a tighter criteria during this data mining process. So I tighten the criteria to 90 percentile of the bin 6 distribution, which equal to 0.187 in this case. So anything that fail or less than 0.187 are defined as a good wafers. If it's above, it's bad wafer, even though they may not to be scrapped. So this is how I define the categorical response in these predictive models. So by doing this, I will have around 200 parameters. They are my good parameters. And I have 1,800 about, they are my good wafers. Okay, so we defined the parameters, the response, and the predictors in the previous slide. And I'm going to introduce you 4 simple model technique in JUMP predictive modeling platform that can help me to do a quick and accurate prediction to make a good decision. So for the categorical response, good versus bad bin 6, I'm going to use the decision tree and the bootstrap forest. The bootstrap forest will again used to predict the regression response, which is my normalized bin 6 fallout. And I'm going to compare to a fit model that is the stepwise linear regression. So after the demonstration of 4 of these models, I will show you that how do we pick which model to use. I will compare the R square and to decide what is the model I'm going to use. And also the benefit of using the predictive model is it's going to give me, hopefully give me the, what are the key class probe parameters responsible for my bin 6 fallout. Okay, so the first step to do the data mining in the predictive modeling is I have 2,000 data set. I'm going to divide it into training data set versus the validation data set. And we can do that under the JUMP predictive modeling. And we have to follow the honest assessment recommendation. So it's good that the JUMP default, which I'm going to show you the JUMP. Yes, we can go to analyze, predict modeling, and we go to the make validation column. Okay, so One thing I want to make sure is, since I have 25 wafer per lot, that they go through the process together, I want to make sure that I have a representative from each of the lot going to the good versus the training versus validation data set. So I was stratified using the source lot, which is my wafer lot ID. And then I will say, okay. And then you can see the default in JUMP is already followed the honest assessment recommendation. 75% for training data set and 25% for the validation data set. So I'm not going to run this here because I already created the column here, validation. Okay, so this is how you can generate your validation column, and we are going to use it for the model that we are going to demonstrate. So let's go back here. And remember that I mentioned I have 150 wafer in the at class probe that I don't have the unit probe feedback. I don't know what is the bin 6 for, and I want to know. So even I put in my test data set using those 150 wafer at class probe, they still follow the honest assessment rule. So I'm good to go. Okay, so first I'm going to show you the classification response using the decision tree. Let's go back to JUMP. This is my data set. So it is under Analyze, Predictive Modeling. So we are going to be here a couple times today. And it's under the partition. So let's click on the partition, and you can see that, yes, I have the decision tree here. This is the method I'm going to use for my predictive model. And I put the validation column I created here. I use the bin 6 class, which is good versus bad. You can see it here. This is my bin 6 class. And I have my 173 class probe data here. I hide it in this data table, but you can see they are 173 here. So let's go click OK. Yes, this is my decision tree. I already pre-colored the bad red and the good blue. So we can, I can show you manually how to do the split first. So the JUMP will do the split based on what is the most significant difference between the good versus bad. Here, it choose the resistance from ISP plus. If it's higher than 148, I have this much more bad wafer than the when we have the resistance less than 148. So this is the first split that JUMP found. I can continue doing the second one, and it found the TXP. If it's less than 145, wow, I have much more bad wafer that can be with high normalized bin 6 fallout with a combination of the higher resistance and the lower thickness. So I can keep doing that manually, or I can do go, and then we can get the JUMP to help me to do the split. So it stopped after the 6th split. Let's look at the R square. So the R square for the training is about 67%. And for the validation is about 60%. Not bad. And there's something here in the red triangle next to the partition for bin 6 class. Okay, I would like to see the column contribution. This is the one that will help me to learn what are the parameters that JUMP summarized for me. So besides the two, the ISP plus and TXP, and we also, JUMP also found two other parameters, but with the last contribution to the bin 6 fallout. So we will close this window and minimize my JUMP and go back to here. So this is the two things I recorded, the R square for this model and the column contribution here. Let's move on to the next model. I'm going to show you the same classification response, but I'm going to use another partition model that is called bootstrap forest. Let's go to my JUMP. Yes. So let's go to analyze, predict modeling, and the bootstrap file is just below the partition here. Validation, we'll go to validation again. And I'm going to do the categorical response, good versus bad here. My predictor from class probe is in the X factors. Let's say, okay. So jump default, again, I'm going to just make it simple. We follow the recommendation from jump. It's going to build 100 tree in the forest. Let's see. So it will summarize, average out the variability. So it is more stable than the decision tree, which is only one tree. Now we got we have 100 tree average out, and we can find the R square here. So generalized R square is tell me that, wow, my R square can be high up to 90% for my training data set, and it's 80% for my validation. So you can see that with the bootstrap forest, it did improve the R square for both the training and the validation data set. We can also go to the column contribution. And yeah, we have the resistors and the oxide thickness highlight again. But besides the total 4 parameter, the bootstrap forest, because it runs 100 trees, it gives us much more parameter, but with very minimal impact to the normalized bin 6, good versus bad. Okay, I'm going to keep this model because it performed better than the decision tree. I will minimize it for now. And let's go back to my presentation here. So yeah, we have very good R square, and we have the 2 highlight parameter. Okay, let's move on to the continuous response. So it is the regression model I'm going to demonstrate here. We will use the stepwise fit linear regression. This is my data table. Go to analyze, fit model. So instead of predict modeling, I'm going to use a fit model. So it's another way to build model. There's no place for me to put the validation because I'm going to use all the 2000 plus data all together to make the correlation. So we say we want to do the regression model. So I'm going to use the continuous normalized bin 6 for in my Y. And I'm going to pick the class probe 173 parameter as the main effect to my model effect. You can do the macro to degree for 2, then now you are going to see the interaction between any of the 2 factors. But it's going to take a long time, so I'm not going to run it here. I'm going just to use the first order. And since I have so many predictors, I like to use stepwise. Yeah, and it's more robust. And run the models. Okay, so again, I'm going to follow the jump recommendation. I'm going to use the minimum BIC as my stopping rule, and the stepwise direction will be forward. So we will keep putting in parameter until it have a good model. So you will run the model, take a few seconds. Yes, after it's done, you can see that I got R square and R square adjust here. And it's around 74%, not bad. Yeah, and those 2 numbers are very close. So let's look at our model. Yes, so this is my model for the linear regression. And it did give me the ISP plus, not highlighted, but the oxide thickness, the other one, it is a little bit low. And I do have a lot of other parameters show some kind of strong correlation to my bin 6 contributed to the normalized bin 6 fallout. This is because that I have a large data set, more than 2000 wafers, so it's easy to find correlation. But we will stop here and then go back to the my PowerPoint. So this is the R square, and this is the effect summary that what parameters are important in this stepwise fit linear regression model. So the next model I'm going to demonstrate, we go back to bootstrap forest. This is a very good prediction model because it can also handle regression pretty well. So let's go to my jump file again. Analyze, predictive model, and bootstrap forest. So if you have used jumps before, you know that we can recall the setting we have. But I'm going to replace the categorical bin6 fallout with my normalized bin6 fallout, which is continuous factors. Okay. And I will again follow jump recommendation to use 103 in my forest. Okay, it will take a few seconds, but not too long. Okay, let's see. The bootstrap forest for normalized bin6, it give me, wow, my R square is around 0.977, 98%. And for my training data set, for the validation data set, I got 91%. This is outperforming the other model I just showed you, the linear regression. Yeah, so I'm going to keep this one. And let's take a look before we move on. Column contributors. Okay, we have the same two resistors and oxide thickness that highlighted, and we have another two that is high, but the others a lot of other parameter with a small contribution to the model. So in this case, if you want to build a reduced model, you can highlight the two parameter here, and you go to analyze, fit model, and then you do macro, and I like to do the response service. Why? Because I capture the main effect, and I also capture the interaction and the quadratic effect. So I can put my normalized bin6 to y, and I will use, because I don't have a lot of predictors here, I will use a standardized least square and run. So this is the model you can get, and then you can reduce from here. So this is a reduced model, which only give me 65% of the R square. So it is good, but yeah, it can be more stable because you don't involve so many predictors, easier to explain the model, but the bias will be higher because it doesn't have all the other parameters that highlighted by the bootstrap forest model. Okay, so let's go back to my presentation. Now we finish all four models, and let's look at the R-squared comparison. It is not very fair to compare the stepwise linear regression because it's not using the same platform, and it's not the training versus validation. It's R-squared versus R-squared adjust. But you can see that my bootstrap forest for both the classification data and for the regression data response are very high, higher than 90% for the training. And it's also the highest for the validation data set. So I decided to use both for my good versus bad prediction and also for my estimation for the bin6 fallout. So then here, let's see, how do I estimate it for it? I go back here, and I remember this is the one for my bootstrap forest for the class data, good versus bad. So in order to use the predictive model, I'm going to the red triangle and save columns. I will save the prediction formula. Then you can see that quickly the jump give me the predict the probability for bad versus good, and then it will say most likely bin6 class here. And if you go to the very bottom of the my data set, then you can see that I have those 150 wafer that I hide it in the data set when I build a model. but the equation that generated by the model apply to those 150 wafers, and it predict, okay, I will have one bad wafer from this lot D, wafer one, and the others, right? So lot C has a lot of bad wafers, and we have lot A with some bad wafers. So it's a very quick way to tell me that how many wafers are at risk. But this one only give me good versus bad. I'm going to see that if I know the what is the estimated bin 6 for, if I can get a number, it will be, it's even better to help me to make a correct decision. Oh, this is not the one I want. So it's this one. Yeah. So I want this one, that is the bootstrap forest for the normalized bin 6 for the regression model. Very similarly, I'm going to show you red triangle and save the prediction formula. And it will give me the normalized predictor here. Let me minimize that one. Okay, so for each of the 150 wafer that is under test in the validation column, I got a predicted number for the bin 6 for. So this is how you use the predictive modeling in JUMP and to give you the estimated number to assess the risk of those 150 wafers. Okay, so in at the end, we know that it's about 47 wafer will be bad, which means elevated spin 6 for, but none of them will trigger the scrap limit. So we decided, okay, we will send down all those 150 wafer to Uniprobe. 4 months later, 4 weeks later, we will get the Uniprobe data and we will review how good is our model. So the decision we have been made is we send down the wafer because we don't need to scrap. None of the wafer will be a scrap risk. And also we don't need to start a new lot because the overall die impact from the estimated bin 6 fallout is not enough to warrant a new part start as a backup. And I also learned that which two parameters are key for responsible for the bin 6 fallout. After talk to our subject matter expert, and team decided we can work on the resistance that is high. We can do a process windowing and see if we can lower the resistance and keep up the yield for the part A. And the other parameter, TX, it's a batch process. You can process with different part under the same technology. So it is not suitable for making process change. So team decided that we are going to tighten the control limit in line, so to ensure we have a stable performance for this TXP. So this is 4 weeks later, we got the Uniprobe feedback from these 150 wafers. And you can see that, yes, we do have a two-lot that is higher fallout for the measured bin 6 percentage. And this is the predict percentage of the bin 6 fallout. So the correlation is about 71%. It is not bad, yeah. So it does help me to make the right decision. And none of them exceed the 0.187 criteria that at high risk. But you can see obviously one lot, the lot C kind of behave odd. So we review the lot processing history and we realize that lot C is not a standard product. It was used for a process change evaluation. So we have to exclude it from the modeling. And with that, we can improve our R-square up to 80%. Yes. So in summary, that I'm looking for a predictive modeling to help me to make a good decision quickly. not using the DOE that take months to get the result out. And this model need to handle the autocorrelation without a lot of data manipulation or limited because of the computer memory constraint. So we talk about the tree partition and the bootstrap forest for the categorical data. They are good to handle large predictors, large number of predictors, and also it doesn't care about the auto correlated predictors either. And we talk about the bootstrap forest, which is outperform the linear regression as well. And it can handle both the classification and the regression data, and very good with large predictor and also good with autocorrelate predictors. So I hope this has been helpful and will help you to try your first predictive modeling using JUMP software. And so you can make an educated decision based on data. So this is the end of my presentation. Thank you for your attention.